Okay, folks. So today we will study cryptographic hash functions. Just a minute. Give me a minute. I think my Apple Pencil again is not working. So let me fix it. Just give me a minute. Okay. Okay. Started working. Actually, I need to sync up in the morning. All right. You can see the screen, right? Okay. So today we'll study the cryptographic hash functions. Okay. And there's a lot of practical it's used in practice. So it's very important. Okay, you can read it from many sources. All books cover this, and I have note that I have used one more book here. It's a very simple book by Mark Stamp. I think he's a professor in some university in US. This is a very simple kind of book, right? So I have in the rest of our course I will be taking some parts from this book as well. Okay, all right. So today, last 2 years have been quite hard for us, and now we are getting world is kind of understanding what the viruses are, and I mean many waves are over, and then this is a time actually we can start roaming around, do things, life may become normal. And then another threat came to the world, which is Russia-Ukraine war. Okay, so this to us, many of us, it appears to be just a normal traditional war. Okay, like two armies or two air forces or two defense organizations are fighting with each other. Okay, this is a traditional war that has been happening for many centuries. Okay, but behind this is another war that's happening. There's a cyber war. Okay, and this cyber war is of course happening in background all throughout, but when traditional war happens, then it intensifies. Okay, so now there is a lot of cyber war happening between two enemy countries, and not only two enemy countries, but also the rest of the world, which is on one side or the other side. Okay, and this is today I've just browsed through newspaper and could find few interesting stuff, right? And you will find hundreds of these. There's nothing. Okay, and then okay, then a lot of things that the hackers either in Russia or Ukraine can pose problem to other country and all across the world, right? Right. There's another one with this war is seen threat to insurers in certain way, and then this is also again today's newspaper. Ukraine cyber war resistance group targets Russian power grid and railways. That's interesting. All right. One way is of course attacking TV tower or something, and second is the disabling it. Just disabling, not make it not available for anybody, which anybody sitting anywhere can do. Okay, with proper tools and so on. All right. So what is cyber war? What is it? Any thought? Yeah. What happens in cyber war?
Causing damage through technology, mostly using digital means like
Yeah,
website, putting on websites and
yeah,
traffics and everything.
yeah. That's good. That's good. So basically, you're very right. I mean, you know, for that, of course, something that's needed is internet. The internet reaches everywhere, right? Just think about it. That if Russian forces have to destroy a TV tower, and which they destroyed, okay, they have to physically come there, right? By air or by on earth, by on surface, uh, to do destruction. Okay, that's true for any two countries, right? But in cyber war, you can be anywhere and cause damage, because wherever the internet is, you can always reach there. And before internet came, this was difficult thing, because there were a multitude of many diverse networks, and it was extremely difficult for person sitting in other country to penetrate into some other country's network, which is again mix of hundreds of networks. Okay, so internet, as you know, works on top of any kind of network, right? It's an interconnected network. I mean, it works on Ethernet or any kind of layer 2 technologies, or even older technologies like T1, E1, or whatever, Sonnet, etc. Right? So wherever internet is available, anybody can penetrate, get into, right? Okay, and of course there is a defense for that also, right? But defense is always, note that defense is always limited. Attack can be from any point, anywhere, and in and overall attack surface is very high. Defense is limited, attack can be anywhere, right? So there's always advantage to attackers in comparison to defense, people who are defending or defense mechanisms. Okay, so cyber warfare is basically done with secrecy. Now, when actually there is a war, then they also declare that we are trying to break. We have broken, and so on, right? Your systems and so on. So bullets and bombs are replaced by malware, denial, uh, denial of service attack, distributed denial of service attack, illegal transfer of funds or freezing the bank accounts, phishing attacks. And this is time where a lot of creativity happens, right? You will find in Ukraine-Russia war, there's new kinds of viruses have come out, okay, which of course are aimed at those countries, but will spread very soon to other places as well. Then website attacks, enemy country's website you take control of and publish your contents or crash it. You crash, for example, somebody can crash a bank's website. That can result into, millions of dollars of losses, because most of the transactions do happen through web technology or web interface. And something that's happening now is that you can cripple down the logistics of that country. See, any country now, most of the countries, I would say every country, but most of the countries, there is a computer behind management and control of operations, right? Okay, like whether it's a city, a normal, in any cities, normal governance issues, governance control, or banking, or electricity distribution, logistic or transport distribution, local transport, okay, healthcare system, all are using computers and internet. Through internet, you can reach anywhere and then attack the computer. And of course, computer controls everything else, right? So logistics, power grid, transportation, etc., etc. So by attacking the computer, you're disabling all these functionalities. All right, so this is happening. So when you read something about it, just Just try to understand what exactly is happening and how it is happening. Okay. And then as a security professional, you have to think how to make or how to design or develop protection mechanisms for this. Okay, all right. So now come back to where we were. Last class we studied block ciphers. Okay, we have studied then basically for AES or DES in encryption mechanism, and note that these are symmetric key encryption. Okay, and we have seen that just using only, for example, AES on a block of some size is not sufficient, because message can be longer than the block size. And secondly, you know, AES, if it's used, because there's a lot of redundancy in data and the key remains the same, then it shows up in the output. Okay, so in order to overcome this, a lot of mechanisms have been used where, and these mechanisms or algorithms use AES algorithm internally. And we have seen these mechanisms like ECB was the first one, wherein just is multiple of block sizes, but this is not very secure. Then we try to introduce randomness. Okay, so we had CBC mode, and then we could see that we cannot parallelize it fully. We cannot, you know, so that it will take less time, and then we came up to CTR mode. All right. So these we have studied. All right. Okay, so today we'll study in brief hash functions. So these are topics that we'll try to cover in remaining 40 minutes, rather 30 minutes. So this is where we are. We have covered this part and we are now coming here. So basically with symmetric key encryption, we are trying to do something about integrity and authentication. So we will study hash functions, which is very important topic. Okay, and it is heavily used in real world. Okay. Now note that you have studied hash functions, hashing also in data structures. Okay. Basically, that hashing is used primarily to improve efficiency of algorithm. You want at the cost of space. Okay, so you want to achieve order one search time, and then you do it through hash. Now that hash function and this hash has no relationship. Okay, these hash functions are called cryptographic hash functions. Cryptographic, right? All right. Okay. So, all right. So hash gives a digest of a message. There is a message. It could be any long. This length could be anything. Maybe a file, or maybe you know, hundreds of megabytes. Okay, and then we want to have a small digest of this, or a small signature of this, or fingerprint of this. Fingerprint is of this one. What is a fingerprint? What does fingerprint is unique? Okay, remember, I mean, I won't think you will remember it, but ask your father or mother whether they have used the actual fingerprint. You know, I mean, you know, so many places, for example, even marriage registration and some other important, you know, or even now it happens in property transactions. Okay, you go to registration office to register your property, they will take your fingerprints. Also happens in airport. Happens also in passport, right? In US embassy, you go for a visa and then they take fingerprints of Earlier it used to be 1, now I think all 5 fingers. So what is unique about fingerprints? In Hindi we used to say angutha laga diya usme. Basically you take a thumb print, and put a ink and then press it on some document. You just make imprint of thumb. Okay. So what is unique about fingerprint of any fingerprint? It's unique to a person. You cannot change it. Your fingerprint cannot match with anybody else's fingerprint in the world. It's impossible. And that's the beauty. Okay. Similarly, can we create a fingerprint of a message? Message could be any message, right? The message here is your choice. It's combination of zeros and ones, of course. It could be a random message, any message. And we create a fingerprint of that. If you change this message, or even if you change few bits of this, then the fingerprint of that will differ. So these two may not be the same, will not be the same. Okay. All right. Just think about it. Okay. And then note that we don't use keys here. It's a keyless. In encryption, we have used keys. Okay. And two important uses of hash function: digital signature and hashed max, which we'll study in the next class. All right. So we'll define hash function as h. Sometimes we use a small h, but mainly a capital H, and m is message. Okay, this for this message, which is the original message, you want to get a fingerprint that is called hash. Okay, so this is m, apply h hashing function, okay, over m, and you get h of m. Okay, so this m could be of arbitrary length, as we said earlier, but the output that you get, this fingerprint of, is of fixed size, which we say of n bits, or it could be anything that you define. Okay, so hash, when you apply hash function on an arbitrary length message or any file or anything, you get output, okay, or hash output, which is of fixed size, which is signature of it. Okay, all right, but note that we are not using key here. Why? Because we are getting signature, just signature. We are not going to reverse it. We are not going to use signature and try to get m. Signature is very small, while m could be a movie itself, right? A file that's containing a digital movie, but a signature is small. So it's basically reverse function is not applied here. So what are the properties? Deterministic. Every time you get a hash of this message m, it will give you same output. Okay. Efficiency. Creating a hash of a message should not take days. I mean, it should be take few microseconds or so on. Very small time. Okay. And is that security properties? There are many security properties that we'll study now. Is a one-wayness. That's also called pre-image resistance. Then second pre-image resistance. We'll study what is pre-image resistance, second pre-image resistance, and then collision resistance. So there are three properties. Okay. Okay. And then the next one is unpredictability. So there should not be, output should not be predictable. Okay, no predictable patterns for how changing inputs affects the output. Means that if you make a small change in input, Output changes will not, it should not give impression about input changes. Could be many bits. So one bit change in input can result in say thousands bits of changes in output or hashed output. Okay, that's the concept. Any question? Basically, you will have to think through just in your mind why key is not required here. If key is not required, this hash function is known to everyone. These all published, right? So what are we trying to achieve out of it then? Anyone? Okay, we'll come to
It is
that.
basically computationally infeasible to compute the reverse hash of n.
Yeah, okay. So one, the reverse of course cannot be done. Okay, that comes into the first property, one-wayness. But what we are trying to send, when we are trying to send a message, say M1, Alice tries to send a message, say M1, she will also compute its hash. Okay, and when it goes to Bob, and this algorithm is known, hashing function, so he will also compute hash of the message M1 that he receives and then compare it with the received hash. If both match, then fine. Though Alice has to send message M and then hash value also. Now, of course, there are various scenarios, right? That can happen. I mean, if Mallory is in between and changes M1 and also hash value, then Bob cannot find it out. So we'll look at those cases, but in general, when hash gives signature of a document or message, and when reaches other end, that person can also calculate hash and both match, then document is genuine. Because if the any single bit is changed in the document, then the calculated hash value will be different. Okay, this is in principle. Now there can be various scenarios that we'll look at it, and there are ways to also overcome those issues. Okay, so practical, as we discussed, is of fixed length. The output should be of fixed length. Then usually it is 128 to 500 bits. No, size of file could be gigabytes, but output is always a fixed size, which can be between 128 to 500 depending on the algorithm. Okay, computed fingerprint should be highly sensitive to all input bits. That's fine. Any change in the message, no matter how small, may change many of the bits of the hash value. Okay, all right. And with no detectable pattern on how output changes based on specific input changes. This point also we discuss. And note that the hash function is not keyed. We don't use key as we did in case of encryption. So anybody can compute hash on any message. Fine. So now pictorially, okay, M could be of, sorry, message M could be of any length. However, the output, hashed output Z is small and fixed. Okay. So basically you, to the hash function, which is here, you give this message and what you get is one chip, like potato chip of fixed size. Whatever be length of the message, output is always the same size. Remember this. Okay, because this gives actually signature or fingerprint. All right. Okay, so if this is a message, okay, which is very big, and apply a hash function here, then you get output of this size. 8 bytes. If it's a very small message, I am not a crook, okay, then they get this one, which is of the same size same. Okay, if you change just one bit of it, drop this letter R, and you say that input message is I am not a cook, and then you can see the output varies a lot from previous, because one letter change may result into huge change in the output. And this is actually taken from hash function. So you can see the difference between these two. Okay, so this is a property. All right. So one example is that document comparison. If Alice and Bob both have 1 GB document, okay, same document is available to both, and they can both compute hash over the document and then securely communicate hashes to each other. Okay, now note the word securely. It means that the hash value doesn't change in between. And if the hashes are the same, the file must be same, since they have the same fingerprint. Okay, if hashes are different, the file must be different. All right. So basically, main idea is that this is a message. Okay, and this bit string could be any length, and then we have a mapping function here. Okay, it's called compression function. Okay, and then it compresses into or n bit string. Okay. Okay. So the H function is a lossy compression function, and however it can result into collision, and which we will discuss later. For some value of input, okay, so take hx or hx dash, there are two inputs here. If both maps to same output or same hash value, then there is a collision. Okay, now note that you cannot avoid collisions, because this size here, message size, could be anything. It could be anything, right? It could be GB, and output size is fixed, say 512 bits. Okay, also all these values here will map into only 512 bits, so there has to be collision. But you have now challenge is to design hash function in such a way that it's very difficult to find collision. It's very difficult to find x and x dash both map. So this pair is extremely difficult to find, which may result into collision. Okay, so we will look now at certain properties. First is one-wayness. Given an input y, it is infeasible to find x such that hx is equal to y. So it means reverse, given you hash value, okay, of whatever size of say 128 bits, from that generating the original message, which could be of GB, etc., is impossible, is infeasible. All right. So what does it mean? Intuitively, it means that given an input of hash function, it is infeasible for adversary to find out any input that hashes into output. It means that from signature you cannot get the original message. Okay. So another way to say is that there is no feasible way to invert the hash. Fine, that's also fine. Okay. And it is very, very hard. If you are doing this, is infeasible. Okay. All right. Brute force method can be tried, but it's very, very complex. I mean, it means that what you have to do, given one value of y, try all possible value of x. Okay. Now this is very hard. This is brute force, right? It may take million of years, right? If the size of y is long enough. Because for each value of y, you'll have to try this. Okay. All right. So this is first property is one-wayness, because given signature or hash value, getting the original one is infeasible. Okay. Second property is called, oh, just a minute. Okay. So this one-wayness is also called pre-image resistance. Pre-image. Then we have second pre-image. Okay. So it says that given one input x, it is infeasible to find another input x dash such that hx is equal to hx dash. It means that in here, given a value of x, okay, and which maps, and h is known, so this maps into, say, y. Now you have to find out x dash, that also maps to y. So what things are given? You have x is given, h is given. From this, it means that y is also known. Now your challenge is to find out x dash, which also hash it into same value of y. Okay. All right. So intuitively, it means that given an input, it is infeasible for an adversary to find out another input that has the same hash value as the original input. Okay. So these two are mathematically defining. So another way from security perspective is to say that it is not feasible to modify a message without changing its hash value. If x and x dash, you can find out x dash. Okay, it means that you can change from x to x dash. You can change the contents of message. So adversary can do that, and yet hash value is same. So if Mallory can change the message and keeping the same value of hash, because hashes are known to both ends. Okay, not necessarily, say Mallory is not able to change value of hash because of some reason, and okay, or she also may not want to because Bob knows value of hash, which happened over secure communication. Hashes are known to everyone. So Mallory in between cannot change the message m to m dash keeping the same hash value. That's the intent. Okay. We also call this weak collision resistance. And then third property is called full collision resistance or strong collision resistance, where it is infeasible to find any pair of inputs x, such that hx is equal to hx dash. Now earlier we were talking only about given one x, can you find out x dash? Now we say then the whole space, can you find any pair which maps into one value, that's y. Okay. So intuitively, it says that it's infeasible for adversary to find any two inputs, and both hash to same value. All right. Okay. All right. So these are basically this definition of collision, which we already discussed. Okay. So can we design a question is that can we design a hash function with no collisions? No, we cannot do that because the original message m could be of any length and signature is small. So there's a possibility it means that there is always collisions. Okay, but the only question is the design hash function in such a way that it's very difficult for adversary to find those. Okay, so we want to make finding collision infeasible for an attacker. Infeasible means that there is no way to accomplish this with any realistic amount of computing power. Of course, if adversary has say millions of years to do that, that's not feasible thing, right? All right. Okay. So a lot of collision do exist, but it's hard to find any. So of course you can observe that collision resistance, the last one, right? Any pair verified is easier for adversary than second pre-image resistance. Okay, because second pre-image resistance you have just given one x and then you have to find x dash, while in collision resistance you have to find any pair of x and x dash. Okay, all right. So collision, as we discussed, collision do exist because input space is much larger than output space. Okay, so consider a function where we generate 128-bit output. Okay, and just input size is just 150 bits. We are not talking about a gigabits here and so on, right? We are just talking about 150 bits. So then you can see we can see that 2 raised power 22, that is almost like 4 million of the values from input space hash into each of the possible output value. Although just message is slightly longer than the hashed output. Okay. So only thing that we can do is that make this finding out collision computationally hard. Okay, so one question. So this class size is, whatever your class size is over 40. Okay, and you have birthdays, of course. You are born in one of the day of the year. What is the probability that two of you have the same birthday? Do you know anybody else in your class having a same birthday as yours? Yes or no? Any of your friend in the class or your senior batch, because there are two batches here, have the same birthday? No? Yashi?
No, sir.
No, okay. All right. What is the, so, but statistically there has to be. Okay. Okay. Other way of putting it is how many people must be in a room before probability greater than half that any two people have the same birthday? Put certain number like this class. If I say probability has to be greater than half, how many people has to be in this class? You can do math, you can do mathematics, and you can just find it out using simple mathematics, probability theory. Okay, and then you can find out 23 people. If you have 23 people in the class, there's a probability greater than half that at least two of you will have same birthday. Okay. All right, and why we are trying to compare birthday? Because it's the same as collision resistance, right? All right. So basically, from this you can find out this is nothing but square root, approximately square root of 365, and so n bit hash will require 2 raised power n by 2 work to break it, where n is the number of bits in output, hashed output. Okay. Okay. So this is, and while you can find it out in case of second pre-image, where given x and you have to find out x dash. You know, it will require 2 raised power n minus 1 attempts or tries, right? Okay. So give, say for example, we say that Yashi's birthday on certain date. Is there anybody in the class who has also birthday on same day? Okay. So this will require more work than finding out any two people who have the same birthday. Okay. So the work here is 2 raised power n minus 1 in case of second pre-image. And while this work is 2 raised power n by 2 to break it in case of third one, which is what is it? A collision resistance. Okay, all right. All right, so some properties when you're designing crypto hash, it has avalanche effect. We have already studied that changing one bit of input should result into, you know, huge amount of change in output. So it says that at least half of the output bit should change. Okay. Okay, hashes work by hashing message into blocks. It means that given one M, you have to break this into blocks and then apply function H on this and get the output N and so on. Okay. Okay, and then similar to crypto, you know, way crypto is designed or encryption function is designed, crypto hash also requires certain rounds of, you know, that mixing, matching, shifting, etc. Okay, so just go through it. Hashing versus encryption. Hashing is one way and there is no unhashing because it's a one-way property. From signature you cannot get the original one. Okay, hash hx looks random, okay, but can be compared for equality with hash x dash. Okay, so hash, so if you hash one value multiple times, you will get the same results, because then there's no concept of key and key can change. While you encrypt the same message multiple times, and we have seen earlier where we include randomness, then output value also changes, right? So these are just a few points to think about. You know, so there are a number of ways to design hash. Okay, it's MD5. Okay, here MD5 output is 128 bits, and security is completely broken now. This was designed many decades back. Okay, so you can see the hash of there's little simulation here. Yeah, you can see hash of its own. Okay, then second one is SHA-1, which output is 160 bits. It means the hash output is 160 bits, and it's completely broken in 2017, but it's still in use. Okay, SHA-2, the output is 256 bits, 384 bits, or 512 bits, and it's currently not broken. So mostly SHA-2 is in use, right? And then next came is SHA-3 and so on. So it's a kind of SHA-2 and SHA-3 both are in use. Okay, so there can, but there is some issue here in hash function, and it's one it allows for length extension attacks. Okay, we'll not go into details of this. Okay, given a message M1 and M2, where M2 is M1 concatenation with some string X. So basically M1 is given. Now M2 is same as M1 with X concatenated to it. So this is called M2 and this is called M1. This is M1. Okay. All right. So now it says that HM2, H of this concatenated message can be computed based only on HM1 and X. Okay. Now HM1 is known, HM1 is known to adversary. Okay. So from this and then if adversary also knows X, then from that she can find out HM1 concatenation with X. Now, how it can lead into some weakness that you'll have to think. But she can given one hash function because it's all done in using blocks. Of course we have deleted that. So concrete we can find out hash function of M1 plus X simply by adding X to original hash. Okay. So this can lead to some weaknesses that you'll have to think through. Okay. Integrity. Okay. It depends on the hash model. Now, simple thing is that that's being used that, for example, Mozilla publishes new version of Firefox. So you can download binary. Okay. So how do you know that you have downloaded it correctly and nobody has tampered this program? Well, this is how you get a malicious program, right? Suppose there is a website looking very similar to Mozilla's website or Firefox website, and you downloaded that software. How do you know that it is a genuine software? So what we can do is that we can use cryptographic hashes. So Mozilla, that binary that you downloaded, Mozilla will find out hash of that and publish it somewhere. Okay. And now you download it from one website and then you go to, for example, some other website where hash is published. Okay, then you create hash of the binary that you have received and match that hash value with the hash value available on the website. So now you notice in many websites hash values are also published. Okay, or you search and you will find it out. Okay, it means that what you are getting as a binary is genuine program. So now what may happen is that now attacker cannot create a malicious program with the same hash value because that hash value is published in some genuine site. All right. Because threat model here assumes that attacker cannot modify the hash value on the website. Okay. So message from this is that we have integrity as long as we can communicate the hash securely. All right. Do hash provide integrity? Again, same question. So it depends on threat model. So Alice and Bob want to communicate over insecure channel. It means that Alice sending message M and also hash of M. Okay. So Bob receives message M and computes the hash on the message. And Bob checks the hash that is computed with the hash sent by Alice. If both matches, it is genuine. The threat model is that in between the mallory can change message and also the hash. So Alice has sent message M and N H of M. She has sent in between. Mallory is in between. It's blocked the message. There's a man in the middle. Okay. And then she has changed this. to M dash and H of M dash. Then Bob receives it. How will he know? He will just calculate hash of M dash and matches with this H of M dash, and will never come to know. There is a malicious message or change message. All right. Okay. So it totally depends on threat model. So, but hash can be used very intelligently as well. All right. So we'll stop here and then start from this point onwards in the next class. Any question? As an exercise, please look at website and see if hash of it is given or not. Hash of the binary software. So you download, for example, VirtualBox. Okay, how do you know you have downloaded from the right website? You search for VirtualBox and then you get multiple websites. You have to know what is the original website, right? Who has made VirtualBox? And then you have to download from that website. Okay, there's a normal process, but many of us are not careful, right? You have downloaded it. Okay, all right. Okay. All right. Any question? Thank you then.